In this question, you're given a tall container. It is open to atmospheric pressure. So let the atmospheric pressure be P0. Contains a layer of liquid L floating on liquid M. We are told that the liquid M have a density which is twice that of the liquid L. So I'm going to use a symbol rho M to represent density of liquid M, and this is 2 times the density of liquid L. And to make the discussion simpler, I'm going to assume that the height of liquid M and the height of liquid L, they are the same. Okay, both are h. So the question asks you to sketch a graph in the space below to show how the pressure P at a point varies with its height above the base of the container. Notice this height is defined from the base of the container. So when you're at the base of the container, the height will be 0. Okay, so if I were to refer to the graph, okay, this will be my base of the container, which is height 0. So to find how the pressure vary with this height above the base, let's consider at the base. The pressure at the base, okay, let me write at the base. So the pressure at the base will be given by the atmospheric pressure, P0, plus the pressure due to liquid L, which is H rho of liquid L G and liquid M. So plus H rho N of liquid G. So that is the pressure at the base when your X is 0. So that pressure on the graph, let's mark somewhere here. So this pressure is given by this expression. What about at a point that is between the liquid that is within the liquid M? So within the liquid M, pressure P will be given by the atmospheric pressure, say at this point, okay, so it will be given by the atmospheric pressure P0 plus above this point there is a column of liquid L, so it's H rho Lg, and okay, this amount of liquid M that is above it, so I will have to plus this height here will be given by H minus the X value, where X is a variable. So H minus X rho mg. So if I were to simplify this equation, I will have P0 plus H rho Lg plus H rho mg minus X rho mg. Okay, if you see this term, it's the same as the one that we have above. So that is the y-intercept. If I were to plot P versus X, so this is the y-intercept, which is the same as this, and your minus rho mg will be the gradient. So the gradient is a constant, negative constant. So the graph from 0 to say h, right, will be a straight line with a negative gradient. Okay, now we do the same thing when the point is within the liquid L. So when it's within the liquid L, the pressure will be, okay, let's say here at this point, the pressure will be P0 plus the pressure due to this column of liquid, which is again given by H minus X rho G. Oh, okay, sorry, it should be 2H because of this liquid M below. So if I were to simplify this expression, I'll have P0 plus 2H rho will be that of the liquid L, G minus X rho Lg. Okay, this term in front is a constant, but it's different from this term here. And if you look at the gradient again is negative and is given by rho G, but the density of L, right, is half that of M. So this is actually half that of density M. So the gradient should be less steep and having a different y-intercept. So if I were to sketch the graph, when it's 2h, okay, it will be like this. If I were to extrapolate the graph, see the y-intercept is a different value, which is given by this expression. Okay, so after 2h, there's no more liquid, it's just air. So the pressure will be constant at P0. So if I were to extend the graph, it will be a constant pressure. So this will be my P0.